Okay guys, in this video we are going to be discussing the temperature dependence of rate constants, which is described by the Arrhenius equation. So rate constants will typically increase with temperature, and the standard way of describing that temperature dependence is through the Arrhenius equation. So here we have our rate constant. It's equal to this pre-exponential factor A times what's called the Arrhenius factor, this e to the minus an activation energy divided by RT. And the activation energy is a characteristic of the particular reaction that you're talking about, as is the pre-exponential factor. It's also called the frequency factor. The activation energy is measured in units of kilojoules per mole, and the units of the frequency factor will be variable, and they will match the units of the rate constant for whatever type of kinetics that you're discussing. So if it's first order kinetics, then the frequency factor will have units of reciprocal seconds. If it's a zeroth order reaction, then the frequency factor would have to have units of moles per liter per second. And so it just depends. This is the exponential form of the Arrhenius equation, and we'll be working with that. There's also this linear form here. You'll notice that if you take the natural log of both sides and then use the rules of logarithms to expand the right-hand side, you can get a form that looks like this. The reason I call this the linear form is that you can plot this as your y-coordinate, and you can plot 1 over t as your x-coordinate, the result of which will give you a linear curve that looks something like this, where the slope of that straight line will be minus the activation energy divided by the gas constant, and the activation energies are almost always positive, and so it's going to be a downward sloping line. And then the intercept is equal to the natural log of the frequency factor. So what you could imagine doing is, if you had a kinetics experiment where you were able to measure the rate constant at different values of temperature, you could take your rate constant at different values of temperature, plot them in a graph like this, fit it to a line, get the slope. That'll tell you what the activation energy is, and then you can use the intercept to determine the pre-exponential factor. Any 2 points along that straight line can be described by this 2-point Arrhenius equation. That's what I like to call it. You'll notice that it has a very similar form to the Clausius-Clapeyron equation and the Van't Hoff equation that we've studied previously, and that's due to this exponential dependence that's common to all three of the different topics that I'm referring to. And so they have a common mathematical structure, and so the 2-point Arrhenius equation looks very similar to the 2-point Clausius-Clapeyron equation and the 2-point Van't Hoff equation. Any 2 points along the line, satisfy the same equation. And so this is the equation for kinetic rate constants. A little bit of the mathematical properties. So just to remind us, a large rate constant means a fast reaction. A slower rate constant means a slower reaction. I should say a smaller rate constant means a slower reaction. The mathematical behavior of the Arrhenius equation: when the temperature increases, that causes the rate constant to increase. And so if you go to the limit of large temperature, so if you take temperature to be infinite, you'll have e to the minus 1 over infinity, which is going to give you 0 in the exponent, which will give you e to the 0, which will be 1. So the very high temperature limit of the rate constant is the frequency factor. So Kr will increase with temperature. For the activation energy, the larger the activation energy, the smaller the rate constant. So as EA gets large, Kr gets small. If you take the limit of small activation energies, so if you take this going to 0, what will happen is the rate constant will again converge to the pre-exponential factor. So that's just some of the mathematical properties. It's really important that you know, how does the rate constant depend on temperature? How does it depend on activation energy? When temperature goes up, the rate constant goes up. When the activation energy goes down, the rate constant goes up. So notice that there's a reciprocal relationship there. This problem is meant to illustrate how the linear form of the Arrhenius equation works. So you have a particular reaction. You're given values of the rate constant at different temperatures. What you need to do is to plot the natural log of the rate constant with respect to 1 over the temperature. Okay? It's going to give you a downward sloping line. The slope of the line will be equal to minus the activation energy over R. So after you do your linear fit, that's going to give you the slope. You can then solve that for the activation energy. The linear fit is also going to give you an asymptote. The asymptote, which I'll call B, is equal to the natural log of A. So you can solve for the asymptote. That is, your linear fit will give you an equation that looks like this, where the slope is minus the activation energy, and B is the natural log of A. Alternatively, you can just take 2 of the data points, and you can use the 2-point Arrhenius equation. Okay, so given the 2 rate constants at the 2 different temperatures, you basically just need to solve this equation for the activation energy. But here's the algebra. And then, like I said, you can take any 2 points from this data set and plug in the values, and it's going to give you the activation energy. To then go back and get the pre-exponential factor, you would then use the linear form You could then take the activation energy that you found here and then take any single point in the data set, plug in the values for K and T, and then find the natural log of A using that approach. So that'll work to get the activation, to get the pre-exponential factor. Here they want us to suppose that we've got a chemical reaction that has an activation energy of 50 kilojoules per mole. They want to know what's the relative increase in the rate constant. What you should do is to take the 2-point Arrhenius equation and then exponentiate both sides. They essentially want you to calculate this ratio. So you would plug in, you'd convert the temperatures to Kelvin, but you would put the 37 degrees in units of Kelvin here, the 25 degrees here, the activation energy goes there, and that's going to give you the relative increase in the rate constant. So what I want to do next is go over a few of the concepts within the Arrhenius equation in more detail, and we'll look at quite a few graphics here to help us interpret them. What is the meaning of the activation energy? Well, the term activation energy refers to the minimum energy that is necessary in order for the reactants to form a so-called activated complex. You can think of the activated complex as a particular configuration of your reactants and products that is in between the reactants and products. So here's a diagram illustrating it. So we've got our reactants over here. So this is potential energy as a function of some hypothetical reaction coordinate. Now, what this reaction coordinate means, it refers to a particular motion between the two reactants. Let's say you've got two reactants coming together, colliding. Okay, so you can think of this coordinate, this reaction coordinate, as the geometric coordinate of the molecules, bringing them together. They start to interact, and then they'll separate into the products. So this reaction coordinate takes us from the reactants to the products, and along the way, this corresponds to some type of molecular motion. It may not be a simple motion that you can describe in just a few words, but nevertheless, it will be a type of molecular motion. Now, notice what happens to the potential energy of the system, as this molecular system, as you move along this reaction coordinate. Well, starting here at the reactants, you see that the energy goes up, it peaks, and then it comes back down and flattens out again, and this is the energy of our products. So the height of this barrier, this energy barrier, that's what we call the activation energy of the reaction. And you can see that there's an activation energy going in the forward direction, and then in the reverse direction, the activation energy would be a lot larger. So there's an activation energy going from products to reactants. The activation energy in the forward direction determines the forward rate constant for a reaction, and the activation energy in the reverse direction determines the rate constant, the activation energy, and also the rate constant for the reverse reaction. Okay, so that's what we mean by the activation energy. It's an energy barrier. It's the energy it takes to get from our reactants to the so-called transition state, the activated complex, which can then fall apart into the products. Think of this region of space here as some intermediate, some transient species between the reactants and the products. Okay, so that's what EA represents. And the larger that activation energy, the harder it is to form the products. And so as a consequence of that, the smaller the rate constant. How does that work precisely? Well, it works due to this Arrhenius factor. Okay, so this is the factor within the Arrhenius equation. It's called the Arrhenius factor. And what it represents is it represents the fraction of molecules that are reacting that have an energy greater than the activation energy. So in order for two molecules to react, they obviously have to hit one another. And so the frequency with which they collide with one another is important in determining how quickly the reaction can proceed. And in fact, that's what the pre-exponential factor is about to some extent. The frequency factor, that's why it's called that, is because it's related to the collision frequency of the reactants. However, not every collision leads to a reaction. Only certain collisions lead to reactions. And one of the factors that affects whether or not a collision will result in a reaction has to do with whether or not the molecules collide with sufficient energy to overcome the activation energy. And so that's precisely what the Arrhenius factor deals with. It's related to the Boltzmann factor, which we've talked about previously at the very beginning of the course. And that's what this represents. It represents the fraction of molecules that have enough energy to get over that reaction barrier. And here's a diagram of how it works. So what we're plotting here are different energy levels available to our molecules. And this curve right here, this represents essentially the Boltzmann curve, the Boltzmann distribution. And so the value of this function, if you think about it sideways, that is from this axis to here, it represents the fraction of molecules that have that particular energy. Okay? And you can see that for low energies, there's lots of molecules that have low energies. And as you go to higher and higher energy, you've got fewer and fewer molecules. That is, the distance to this axis is smaller and smaller. And so that corresponds to less and less population with these higher energies. Well, we're interested, from the kinetics perspective, we are interested in what fraction of all of the molecules have an energy greater than this activation energy. Okay, so we want to know essentially what's the area beneath this curve going in if you think sideways, going this direction. So what's the area under that curve to this axis? Well, that's what the Boltzmann distribution, that's what the Arrhenius factor represents. It represents the fraction of molecules that have sufficient energy to overcome that activation energy. And here is a little problem dealing with that. So they want us to do a calculation with the Arrhenius factor. Calculate the fraction of molecules with an energy greater than this activation energy. And it's very easy to do. E to the minus the activation energy divided by RT. Here's my calculator. So if you take e to the minus 50 kilojoules per mole, and then you divide that by 8.314 times 10 to the minus 3 kilojoules per mole Kelvin, and then multiply by 298 Kelvin. All of that is in the denominator. So we're going to I think we're going to get a very small number here. 1.72 times 10 to the minus 9. So that's the fraction of molecules in your sample, pretty small, that have enough energy to overcome that particular activation barrier. Let me just check my math again, make sure I didn't make a mistake. Nope, that's the answer that I got. So in this case, that's what you get. But for a different temperature, let's suppose that you, I don't know, raise the temperature up to 1,000. If we repeat the calculation for 1,000, you get something like 2.4 times 10 to the minus 3. So a larger fraction of molecules, much larger in this sense. So essentially that's how the Arrhenius factor works. The larger the temperature, the larger the population will be above that activation energy. The last point here on the slide, the effect of a catalyst. So a catalyst is a species that takes part in a reaction, but it is not consumed by the reaction. So it's involved in the reaction, but it's in a sense recycled. What the catalyst does is it alters how the reaction proceeds in such a way to make the reaction proceed more quickly. That is, it increases the rate of the reaction. And so as a consequence of that, it must be lowering the rate constant somehow. And what it does, the way we imagine it, how it works, is that it lowers the activation energy for the reaction. So here we've got two reaction pathways, a catalyzed and an uncatalyzed pathway. And so the uncatalyzed pathway we see here has a large activation energy. Okay, so that reaction, relatively speaking, will proceed slowly. However, when there's a catalyst present in the reaction mixture, what happens is that the activation energy is lowered because there's a different pathway for the reaction to proceed that has a lower activation energy. Consequently, the rate constant will be larger for this catalyzed pathway, and the rate of the reaction will be faster. One thing to notice that they point out down here is that the activation energy for both the forward direction and the reverse direction, the activation energies in both directions are lowered. Okay, and that's significant because a common misconception, or at least it's regarded as a common misconception, is that people will assume that a catalyst can be used to increase the yield of a reaction. That is, maybe there's some magic catalyst out there that I could find that's going to take me from a reaction with a 10% yield of product to a reaction that has a 90% or a 99% yield of product. And that's a fallacy. That's not true. What controls the yield, that is the amount of products versus reactants that you have at equilibrium, that's governed by the equilibrium constant for the reaction. And equilibrium constants, as we've learned previously for reversible reactions, are expressed as a forward rate constant over a reverse rate constant. And so what we're seeing here in this demonstration of this figure, if you use a catalyst to lower the activation energy, it's going to decrease both the forward rate constant and the reverse rate constant by the same amount. And so the equilibrium constant will be unchanged. In fact, what governs the equilibrium constant is the energy difference between the reactants and the products. Okay, and you'll see that those are unchanged. That is the energy difference between the reactants and the products. That is unchanged by the presence of a catalyst. Okay, so there's no such thing as a magic catalyst that'll take you from 10% yield of products to 99% yield of products. What the catalyst is going to do is it's going to speed up how quickly you get to that 10% yield. And who knows, maybe that's enough savings. The time savings alone, maybe that's enough to make your process profitable. Probably not at 10% yield, but you never know. So here's an example involving catalysts, and they are asking us to look at the ratio of rate constants for a catalyzed versus uncatalyzed reaction. So they want us to calculate this ratio, catalyzed rate constant over the uncatalyzed rate constant. And so we would have the frequency factor for the catalyzed rate constant, e to the minus the activation energy for the catalyzed rate constant over RT uncatalyzed. What do they say? They say that the catalyzed rate constant decreases by a factor of 10, as does the activation energy. So this is going to be 1 over 10 times A uncatalyzed in the numerator. And this will be e to the minus, this will be EA un, divided now by 10 RT. Okay, so those cancel. We get this 1 over 10 out in front, and then we're going to have EA un over RT out in front, and then we'll have, it'll be 1 over 10 minus 1, I believe. Yep. And so let's see, the original activation energy was 80, so we'll do 1 over 10 e to the minus 80 kilojoules per mole over 8.314 times 10 to the minus 3 kilojoules per mole Kelvin, 298 K. Let's see, negative 9/10. So starting here, 80 divided by 8.314 to the negative 3, divide that by 298, take it times 9, divide by 10. Okay, that gives us e to the 29, so this is going to be a very large number. Divide that by 10, and we get an increase in the rate constant of 4.2 times 10 to the 11. So that's a huge increase in the rate constant. Okay, so the catalyst is going to make a huge difference on how quickly this reaction proceeds. Enzymes are very efficient catalysts. Well, I'm going to go ahead and stop this video here, and we'll pick up with the next one. We'll discuss reaction mechanisms in more detail.